Hello students, this is the video solution for exam 2. And this first problem is a child swinging back and forth, and you can see that she swings at a height here defined by that angle of 50 degrees. At this point, her speed is 0. This is very similar to quiz 5, where we had a ball being suspended by a string and another string. You cut this one over here, and then the ball starts with speed 0 and then swings this way. So it starts as an NTB problem. This is the n-axis. Should label that. This is the n-axis. mg is going down. Mg cosine theta looks like that way. Sum of the forces normal is mass times acceleration normal, which is mv squared over rho. However, v is equal to 0. And you solve that for 126 newtons each. Now the swing goes down here. The maximum normal force is at the bottom. We got 2t minus mg, mv squared over rho. Let me scooch that up a little bit. If we only know what that velocity was, we could solve that for the tension. However, so we use energy, and here we're looking for the delta mgh. mgh is equal to 1/2 mv squared. You find that and you solve that problem. All right, this is a combination energy and momentum problem. We know it's combination because if I start with some spring energy, when it expands, the bullet goes that way, the gun goes that way. However, so I got 1/2 ks squared, got some energy, kinetic energy. When I put all the numbers in here, I got two unknowns. Both the velocity of the gun and the velocity of the bullet are unknown. We know that conservation of momentum also applies. Starts with 0 momentum. And then the ending momentum are those two velocities, two equations, two unknowns, and you can solve. All right, this is a basic impact problem. Did quite a few of these as well. Here you identify the line in the plane. That's the start. Those are the two mass centers, so this has got to be the line. The plane is perpendicular to it. This one doesn't have any plane velocity before impact. Therefore, it doesn't have any plane velocity after impact. This one, however, does. It's got a component in the plane, and that'll be the same speed in the plane afterwards. So we do the plane first. VA plane 1 is equal to VA plane 2 for particle A, 0. Plane 1 is equal to plane 2 for particle B. I got the 4/5 component of that 4 going up, and that'll be the component afterward. Along the line, the conservation of momentum applies, and the coefficient of restitution applies. So you just plug those things in there. You have two equations, two unknowns. A lot of students got mixed up with the negatives here. So let me scooch that back down again. The negative is important to understand. You have to define positive. I went positive this way, which meant that this one started with a negative velocity. This one had a positive velocity. But when you plug it into the equation, because VA line 1 is first, it starts with that negative, and that's important to keep track of. The energy loss, if you begin with some energy and you have some energy afterward, this is of both particles. You have to look at all of the 1/2 mv squared at the beginning, which are these two for both particles. The 1/2 mv squared at the end is both particles again, and the difference is going to be the energy loss, and that's around 52%. All right, this is a conservation of momentum problem. Straight up, conservation of momentum. You have some beginning momentum. Let me scooch this down just a little bit. You have some beginning momentum. It says that everybody is moving to the right. So 600 pounds are moving to the right. Here you define this as positive. Probably should do that. Positive going in this direction. So I got some beginning momentum. That's going to be the ending momentum as well. Got three equations, or three unknowns in this one, so therefore I need to have two more equations. So we'll use the relative equations for that. Relative velocities apply. Now this is just an important note, is that when you put these things together, it's easiest if you just use all pluses, all positives in the momentum equation. And then when you do the velocity equation, you do the same, or the relative velocity equations again. Do it this way. A lot of students got mixed up with trying to do negatives and stuff like that, which end up sometimes works and most of the time you get the wrong answers. But anyway, so the velocity of A is going, she's going to go, or he, whatever, is going to go in this direction. But rather than put a negative in here, I'm just going to velocity of A is equal to the velocity of C. And it says that A has a relative speed of 5. So again, you're looking at A. This student is going to go in this direction, so that would be -5. B is going over this way with a +5. Putting those properly together and then doing 3 equations, 3 unknowns, and you can find the answers. This is probably the most difficult problem. This is an energy problem with some friction. And so we'll start with the energy equation. I put the datum at the beginning of the problem for both particles. There is some friction. I'm assuming that it's going down this way and that the friction force is going this way. There's work. The only work is the friction force. At the end of the problem, we're going to have some kinetic energy of both particles and change in mgh of both particles. So the kinetic energy is 1/2 mv squared of A, 1/2 mv squared of B. And here's where the pulley ratio has to be understood, is that as this one goes down, this one goes up. If you look at this, this has got 4 p's, that's got 1 p, and you solve that for the distances and for the velocities, and when you plug the pulley ratios into the velocity equation, you just have to do it that way. Same thing with the mgh's. If this goes down 2, this goes up 1/2. And so the HB is 1/2. Now, VA moves down 2, however, the H part is only the 3/5 component of it. So anyway, a lot of people got that mixed up as well. And anyway, you plug all those things together and then you got VA is equal to 1.5. All right, this was not necessarily, or wasn't intended to be a trick, but it was intended to be, you need to check all conditions. And this is a general statement to you. Make sure you check all the conditions or all of the things that are appropriate here. So anyway, so I've got a speed here. Oops, come back here. Got a speed at the bottom. And I want to have to make it around there and make it around here. You'll have to have enough speed at the top to make it safely over the top. So I solved for this to find out that. This is an NTB problem. You find out what speed has to be at the top using the normal force going to 0. That's the minimum speed required at the top. Then you can solve for this one at the bottom, which was what was it, 28.36 using energy. Now, how far does that go? Once you can safely get over here, you can find out how far you go. And if you can go up past h is equal to 40, then that means you can safely make it. So that's what I did. I solved for h here, and h is 41. So it did make it to past point D. And a lot of students unfortunately skipped more than half the problem. If you skipped this condition and just assumed, oh, how much speed do I have to have here to get up to 40 meters, again, you solved an important part of the problem, but only about half it. So I dinged you pretty bad if you skip that check. If you skip the step where you have to check that.